All right, let's just dive right in. At the absolute edge of what we understand, where space and time kind of fall apart, there's one of the biggest unsolved mysteries in all of physics, the black hole information paradox. But today, we're not just going to stare at the problem. We're going to look at a brand new, totally radical, and get this, surprisingly testable idea for how to solve it.
So think about it like this. Imagine you write down a story, every single word, every character, every plot point, and then you throw that book into a black hole. Is that story just gone? Wiped from the universe forever? Or is it somehow still out there? This isn't just a philosophical question. It's the central mystery at a cosmic crime scene, and physicists are the detectives trying to solve the case of the missing information.
And this case is so tough because the two main rulebooks we use to run the universe, well, they give us completely opposite answers. And we're not talking about a minor disagreement here. This is a deep, fundamental clash between the two pillars of modern physics. And this is where the battle lines are really drawn. On one side, you've got quantum physics. It digs its heels in and says information is eternal. You can scramble it, you can burn it, you can shuffle it, but you can never, ever truly destroy it. Then, on the other side, you've got Einstein's general relativity, which tells us a black hole's event horizon is a point of no return, a one-way street. Anything that crosses it is gone from our universe. For a long time, physicists could kind of ignore this contradiction, but then Stephen Hawking dropped a bombshell. He discovered that black holes evaporate. They shrink and eventually disappear. And that just makes the problem 1,000 times worse, because now you have to ask, when the black hole is gone, where did all the information go? So this case of the missing information has been cold for decades now, but that doesn't mean the detectives haven't been busy. They've rounded up a few of the usual suspects. These are the leading theories that try to explain what's going on. But as you're about to see, every single one of them comes with a pretty serious catch. Let's run down the lineup. First, you've got the firewall theory. This one is pretty brutal. It says, yeah, the information is saved, but only because you get instantly vaporized by a wall of pure energy the moment you touch the horizon. I mean, it saves the information, but it completely breaks one of Einstein's core principles, that falling into a black hole should be, well, uneventful. Then there's the really wild one, ER equals EPR. It's a mind bender that suggests particles are linked by tiny wormholes, but it needs a whole lot of exotic, totally unproven ideas about the very fabric of spacetime to work. And finally, you have soft hair theory. This one feels promising. It says the information gets encoded on the surface of the horizon itself. Great idea, but nobody's figured out how that information actually gets out. So, the case remains cold. But now, a totally new clue has been dropped on the table. A proposal that doesn't just re-examine the evidence, it suggests we've been looking at the entire crime scene all wrong from the very beginning. This brings us to a huge question. We've always thought of a black hole as having a definite inside and a definite outside, with the event horizon as the border. But what if that whole division is just an illusion? What if they're actually connected, like two sides of one single twisted piece of paper? Now, to get this, you have to think about a pretty weird kind of shape. It's called a non-orientable surface. The most famous example, of course, is the Mobius strip. You know the one. You take a strip of paper, give it one half twist, and then tape the ends together. If you were a tiny ant walking along that strip, you could just keep walking forever and you would cover what seems like both the top and the bottom without ever having to cross an edge, because there is no top or bottom, it's just one continuous side. Hold on to that idea. So here's the big proposal. At the quantum level, the event horizon of a black hole behaves just like that Mobius strip. If that's true, then there is no inside for information to fall into. Information that gets to the horizon just stays on this single, continuous, twisted surface. It never actually leaves our universe, because there was never a separate interior to go to in the first place. You know, the paper itself puts it perfectly. It says, information is never destroyed nor escapes. It always lives on a single 2D manifold with a parity twist. The information isn't lost, and it doesn't need some magical way to escape. It's always there, just living on this twisted boundary. The twist is the information. Okay, so if you're going to propose something this fundamental, you have to check the math. For decades, the information content, or entropy, of a black hole has been described by this really beautiful, simple formula. It basically just says that the info is proportional to the surface area of the event horizon. The Klein Horizon idea doesn't throw that classic formula out. It just adds a crucial new piece, this K of G, the twist factor. This little term accounts for the information that's stored in the actual twistiness of the horizon.
If there's no twist, K is just 1, and you get the old formula right back. But if there is a twist, this factor tells you exactly how much it's contributing to the black hole's information. Okay, this is where it gets really, really exciting. I mean, a wild new theory about black holes is one thing, but this one comes with a recipe, an instruction manual for how to actually test it. Not in deep space, but in a lab, right here on Earth, and probably in the near future. This is what makes it real science. So how in the world do you test a black hole? Well, you build an analog one. It's incredible. Scientists can take a cloud of atoms and cool them down to just a fraction of a degree above absolute zero. It's called a Bose-Einstein condensate. Then they get this super cold fluid to flow. At a certain point, the fluid flows faster than the speed of sound within it. So for a sound wave at that point, it's trapped. It can't escape. It's created a sonic horizon that mathematically behaves exactly like a real black hole's event horizon. So the experiment would basically go down in a few key steps. First, create the sonic black hole. Then, and this is the genius part, use really precise lasers and magnetic fields to literally engineer a Mobius-style twist into the boundary of the sonic horizon. The next step is to measure the quantum correlations between the little sound particles, they're called phonons, that escape and the ones that get trapped. And finally, and this is absolutely critical, you run the whole experiment again, but without the twist, as a control. Then you compare the results to see if the twist made a difference. The key here is that they know exactly what they're looking for, a smoking gun. In a normal, untwisted setup, you expect to see the standard particle pairs that Hawking predicted. But if the Klein Horizon theory is right, the twisted version should show something extra, a very specific parity twisted signal in those correlations. The entanglement should change in a way that's directly proportional to the amount of twist. It's a clear, predictable fingerprint that has no business being there otherwise.
And they're not just looking for some kind of signal. They're aiming for unbelievable precision. The goal is to either detect that twist factor or prove that it's smaller than this tiny threshold of 1%. This is what makes the theory falsifiable. If they run the experiment and find absolutely no twist-induced signature at the sensitivity, then the simplest version of the idea is ruled out, and that's how you make real progress in science.
So let's just zoom out for a second. What would it actually mean for physics, for our entire map of reality, if they run this experiment and find out the twist is real? The implications are just profound.
So why does this idea matter so much? Well, first, it offers a really elegant way out of the paradox without the violence of firewalls or the super exotic geometry of wormholes. It also saves Einstein's idea of a smooth, drama-free trip across the horizon. What's also really cool is that it doesn't just throw out other good ideas. It seems to be compatible with big frameworks like software and holography. But honestly, the most important thing is that this isn't just a cool story. It's a concrete, testable, falsifiable scientific hypothesis. And that just leaves us with this fascinating final thought. For decades, we've imagined these incredibly complex, violent, or bizarre solutions to one of physics' deepest problems. But this new clue suggests the answer might not be in some new force or some hidden dimension. It might just be hidden in a simple, elegant twist in the very fabric of space-time, a hidden geometry that turns inside and outside into two sides of the same cosmic coin.